Welcome, ladies and gentlemen, to a small demonstration on how to perform a linearization of an HSense unit. The first thing that you're going to need is a gas divider. In our case, we're using a product from IAS. It's found under www.hovercal.de. This is a mass flow controller based gas divider on which we are going to connect 100% nitrogen supply to our first mass flow controller. And we're going to use 100% hydrogen supply to mass flow controllers 2 up to 4. Each of those mass flow controllers has a different flow range in order to establish the gas divisions necessary to produce all the concentrations that we are going to need. The outflow of the gas divider will then be connected to the sample port of the HSense. This is what we see in the second picture. So we're going to have our outflow line from the gas divider directly connected to the sample port. And we have our sample out and vacuum out ports connected to a venting line, which is then guiding the gas safely out of the room. In order to re-establish a full linearization of an HSense instrument, we are going to concentrate on the 2 default setups that are usually delivered with an HSense unit. So we're going to have one setup with 0 to 100 volume% of hydrogen, and we have another setup that is capable to measure from 0 to 50,000 ppm. Your gas divider should be capable to produce the concentrations which are listed here for the 0 to 100% setup, and the concentration listed here for the 0 to 50,000 ppm. In the following demonstration on which steps are necessary to do this, we are going to use exactly these concentrations. So what we see here is the control software of our gas divider. We see here the settings for the different mass flow controllers used. So we have a 100% nitrogen supply on the mass flow controller 1, and we have 100% hydrogen supply on mass flow controllers 2, 3, and 4. And this is where the concentrations can be set. We're going to use a total flow of 2,500 milliliters per minute. This is combined flow of nitrogen and hydrogen. And as we're going to see here, by setting a value on the gas divider, for example, 10%. So this will now produce a 10% hydrogen concentration in balanced gas nitrogen. And we see on the right-hand side, this is our V&F client connection to the HSense. We are currently running the 0 to 100 volume% method. And since we've just applied 10% of hydrogen, we would expect a certain response on our instrument. The first step that you're always going to do before you want to completely re-establish a linearization is to check if the factory linearization is still valid or not. In order to do this, we are first going to run pure nitrogen, so 100% nitrogen over the instrument. And we are going to check the calibration of the instrument. As we see here, since we are using an HSense with a gas cooler, we need to give the instrument some time for the signal to saturate. This can be easily checked by directly looking at the currently displayed value. So we see that we are approaching the 0 value quite nicely. And for the next step, we're going to apply the maximum range that the setup is capable. So in this case, we have a 100 volume% setup. So we're going to take our gas divider and apply 100% of hydrogen to the instrument. Now we should see a sharp increase in signal, since now the 100% hydrogen is supplied to the HSense. And again, we're going to have to give the instrument some time to saturate the signal, which we see right now. So as it's displayed here, we are applying 100%, so the calibration is still very decent. Still, if this is not the case, for a short demonstration, in order to recalibrate the instrument, we're going to right-click. We're going to select the calibration tab. Then we're going to select span calibration. And we're going to enter the actual concentration that is applied to the instrument, which is 100 volume%. And click OK. Calibration will be immediately taken into account. This is displayed here in this small kink in the measurement data. And so now, in order to check if our calibration, our linearization is still valid, we can apply a random point within the measurement range. We can use, for example, 25%. So what we want to have now is actually to check if the instrument displays the value that we have set on the gas divider. So right now, this has been purposefully done. So we see that the reading of the instrument is off by quite a significant amount. So we are displaying now 27 volume% instead of 25. In order to recheck that, we can also try on another concentration, for example, 50 volume%. So here again, we see that currently the instrument is not displaying the set value that is given by the gas divider unit. So we are roughly 5% over the set value by showing 52.5 instead of 50. This would, for example, give an indication that a complete relinearization of this method is necessary. So what we're going to do is we're going to go back down to 0 concentration. So we're going to supply the instrument with pure nitrogen. And now, in order to re-establish linearization of a method, we're going to have to right-click this method and select Edit Setup. This will open the method definition. Next step is we're going to have to go to the Enhancement tab, where we're going to find one single enhancement which holds the linearization for the hydrogen molecule. And we're going to have to go to this Details tab for the linearization data. This is where the previously established linearization is displayed. So these are all the data points that have been used. And you see here, these are exactly the concentration values which have previously been shown in the presentation. So in order to re-establish all of these points, there are 2 ways to do this. You can either use the exact same points in order to do the relinearization, or to be on the safe side, you can also delete all of the points which are currently in the linearization table. So I'm just repeatedly clicking this delete button. And the only 2 values which will remain is stable point 00 and stable point 100, 100. This means there is no linearization going on right now. So once all of these points have been deleted, we can confirm the deletion with OK. And we have to confirm the changes to the method again by clicking OK here. So now the process that we are going to follow is we're going to start with an ordinary 2-point calibration. The next step will be we're going to divide our gas from our gas divider in the stated points, and we're going to perform enhancement calibrations for each and every concentration that we apply. So the first step will be, currently we are running 100% nitrogen over the instrument. We're going to do a right click, then go to calibration. Then we're going to perform a background calibration once the data shows saturation 100% nitrogen. Again, this is taking effect immediately. So once we click on background calibration, we should see that the value goes down to 0 or very close to 0. The next step will be, again, we're going to apply the maximum range that the method is capable. In this case, this will be 100%. Again, we're going to see that our signal is rising. We're going to have to wait for this signal to saturate in order to perform a span calibration. So what we're going to do is we're going to wait for this transient that we currently see to even out. Which is happening right now. So once we see that we get stable results with time, what we can do is, again, right click, go to calibration, then we will select span calibration and enter the current concentration, which is 100%. This will again take effect immediately. So now we have established a 2-point calibration. What we're going to do now is we're going to use the gas divider in order to produce the other concentrations which were in the list in the presentation, starting with 90. So what we see here is that once we switch the gas divider to 90% hydrogen, we see a rather large deviation, which is why we're going to establish the first linearization point in our linearization table. Again, we're going to have to wait until the signal is saturated. So we don't want to calibrate in any of this transient part, but we want to calibrate the point once the signal is saturated. This is now a different type of calibration. So we're going to again right-click, select the calibration tab, but this time we're going to the enhancement add data point section. And here we're going to add a point to the H2 linearization. Looks quite the same. So what we're going to do is we're going to have to tell the instrument which concentration is currently running, which is 90%. And we're going to click OK. This will, again, it will take effect immediately. And now we have added 1 point to our linearization table. We can check this really briefly. So we're going to go back to the setup definition. We're going to enhancements and check what we see. So we see now we have established 1 point. This already makes a sort of crooked line because the system will now try to interpolate from 100% to 0, but it's more diligent to have more than 1 point, of course. So we're going to go further down in concentration and add all these points to establish the correct linearization curve. So our next point will be 80. Again, we're going to see the signal will change rather abruptly once the new concentration arrives. Again, we're going to have to wait for all the transients to disappear until we have a very stable signal. And then we're going to do the same process again. We're going to right-click, go to calibration, then we go to enhancement at data point, click H2 linearization, and now the current concentration is 80 volume%. And we're going to confirm this with OK. So now we have added our second point into the linearization table. And this is now a very repetitive process. So we're just gonna set the concentrations according to the list provided, and we're gonna add each of these points to the linearization table. Process remains the same. We are waiting for saturation on the signal until it is nice and straight. And once the signal is saturated, we're going to right-click, calibration, enhancement at data point, H2 linearization, and we're going to enter the current concentration, which at this point is 70. Once this is done, we're going to the next concentration. So we're going to continue on. And one thing, if you're using mass flow controller based dividers, is what you have to keep in mind. So typically, so all of our mass flow controllers carrying the hydrogen have a certain range, which means there is a minimum and maximum flow rate that they can output. So once you reach the edge of the mass flow controller on the lower side, we switch to the next one because this one can go further down and this one can go even further down. So it's just the difference in maximum and minimum flow that we have for each of the mass flow controllers. Again, right now we're at 40, so we're going to add this point as well. Set the mass flow controller to the next value. So what we see now here, at 20 volume percent, we're already at a set value of 500 milliliters in this case, and we see that the lower edge of this mass flow controller is 100. So we're going to change to the second mass flow controller on the next step, but only after we have added also this point to the linearization table. It's again the same process, right-click, calibration, enhancement at data point, H2 linearization, and enter the concentration that you have set on the gas divider. So what we're going to do now is we're going to switch off this mass flow controller, and the next concentration, which will be 10, will be applied on the mass flow controller 3. And the process remains the same. Now the stepping changes a little bit, so we've decreased from 90 down to 10 in steps of 10 volume percent. And at the lower edge, we're going to decrease in 2 volume percent steps. So the next step will be 8 after the 10 volume percent. Still, our process remains the same. We wait for signal saturation, and we go through our enhancement at data point calibration step. We're going to reduce to 6. next step will be 4. And here again, next step will be 2. Now checking for the ranges for these mass flow controllers, we see that we are almost at the edge of our mass flow controller 3, which has a minimum flow rate of 20.46. So in the next step, we're going to switch over to our mass flow controller 4 in order to do the last 2 steps. And we don't want to forget to establish this point before we switch. Again, we're going to go to 0 concentration on mass flow controller 3. And our last 2 points will be 1 volume %, which we're going to use the mass flow controller 4. Again, we're going to wait for saturation of the signal. Go through the same process. And the last point that we typically use in our factory linearizations is 0.5 volume % for this method. Once the signal saturates, we're going to add this last linearization point to our linearization table, which means now the process of linearization is completed. We can switch the gas divider to pure nitrogen in the meantime in order to check if all the values have been correctly accepted. We can go again into the method definition, go to the enhancements tab, then check the data in the details of the linearization for the H2 molecule. So we should see here at the output column all of the values that we have used, which means from 100 down to 10, then 8, 6, 4, 2, 1.5 have all been accepted, and the linearization curve has been established. And now in order to check if our linearization process was successful, the secondary step is usually always to use points that were not in the linearization table and just check some random points and see that the instrument displays its readings within the defined accuracy for this instrument. So for example, we could go to 35 volume % on the gas divider. So 35 was not one of the concentrations used, so we used 14, 30, and what we want to see is that the instrument now reads the correct value for the applied 35%. And in order to get a statistical estimation of that is you would save these data, then evaluate the reading of the instrument, and then compare it to the set concentration. So usually it is you build the difference between set concentration and measured concentration, and then scale that with the set concentration in order to get a percentile value. And that should be below 2% for these kinds of instruments. Again, you can try different concentrations. So now going down from 35 to 15. take one further up, 65. So we see now that after the re-establishment of the linearization, the points that we supplied, so the concentration supplied outside of the points used for the linearization, all read correctly and within spec, which means the linearization was successful and the instrument is again fit for duty. The amount of points that you want to check on is pretty much within your own quality standard. What we do is we usually have around 8 points spread throughout the complete measurement scale of the instrument. And each of these is available to you on the analyzer record of your instrument. Okay, so I thank you very much for your attention, and I hope this video helps you to be able to check your linearization and, if necessary, also relinearize your instrument. Thank you.